If we have a second order differential equation and we form the auxiliary quadratic am squared plus bm plus c, and we solve that quadratic and we get two roots, m equals m1 and m equals m2, then we know that the function y equals e to the m1x, any amount of that, plus b e to the m2x will be a complementary function for this differential equation, in the sense that if we put it all in here, it will all cancel itself out, make 0, leaving the pi free to create the f of x on the right hand side. Now that's great so long as m1 and m2 are real and distinct, but in the other video I told you that if m is and m1 and m2 are complex conjugates, alpha plus or minus I beta, complex conjugate roots, then the shape of the complementary function would be this: e to the alpha x, a cos beta x plus b sine beta x. And in this video I'm going to prove to you that that's true. I'm also going to prove that if your m comes out to be a repeated root, then it makes sense and is justified to define the complementary function to be any amount of e to the mx plus b times x, any amount of e to the mx. So I'm going to prove that that is a solution, that is a complementary function. It does make sense as a complementary function. So let's start with the general form of the complementary function, a e to the m1x and b to the m2x, and let's, instead of m1, put in alpha plus I beta, and instead of m2, put in alpha minus I beta. So that gives us y equals a e to the alpha plus I beta x plus b e to the alpha minus I beta x. And to be honest, it's okay to leave it like that, but this is how you fiddle around with it to make it into the form that we tend to use in FP2. We're going to use our GCSE rules of indices to pull that into the e to the alpha x, e to the I beta, or in this case minus I beta x, and then we're going to use Euler's rule that e to the I theta is cos theta plus I sine theta. Can you use that? Actually, I'll tell you what, first I'm going to pull out e to the alpha x. E to the alpha x, then I've got a e to the I beta x plus b e to the minus I beta x, and now I'll use Euler. Y equals e to the alpha x, and then I've got a cos beta x plus I a sine beta x plus b cos minus beta x plus b I sine minus beta x. Now, cos is an odd function. No, it's not, it's an even function. It's an even function in the sense that if I've got x here and minus x here, then cos of x is going to be the same as cos of minus x. So this cos of minus beta x here I can change to just cos of beta x. Sine is an odd function. So if I've got x here and minus x here, then sine of x does not equal sine of minus x. Actually, it's going to be the opposite sign. Sine of x will be minus sine of minus x. So this sine of minus beta x here I can change to minus sine of beta x. That gives me the following: e to the alpha x, a cos beta x plus I a sine beta x plus b cos beta x minus b I sine beta x. And now I can join together my cos and sine beta x's. So I've got e to the alpha x, and I've got a plus ib cos beta x, and I've got a minus ib sine beta x. But a plus ib and a minus ib are just numbers, just an amount of. It says any amount of cos beta x, so I can just use the letters a and b to represent that. A cos beta x plus b sine beta x. And that proves that these are the same thing. They're exactly the same thing whether you've got real distinct roots or complex conjugate roots. The complementary function is actually identical. It's just that we write it in a slightly different way. We write it like this in terms of the real and imaginary parts of the complex conjugate roots. Now let's say that our auxiliary quadratic am squared plus bm plus c has a repeated root m equals r. Now that means two things. It means that really, if I wanted to, I could factorise this quadratic as m minus r times m minus r. Probably have to do a bit of work to get to that point, but I definitely can because r is a repeated root. Now if I expand that out, I get m squared minus 2rm plus r squared equals 0. So this means that because I've got repeated root r, this quadratic, am squared plus bm plus c, can be written like this, m squared minus 2rm plus r squared. Now if I divide this one through by a, I can work out what each bit is in terms of a, b and c. So m squared plus b over a m plus c over a is 0. So this gives me a nice little formula that I can use, which is that minus 2r must equal b over a, or rather minus 2ra equals b, or put another way, b plus 2ra equals 0. So this is a really useful fact. If I've got a repeated root r, then the fact that I'm going to use is 2ra plus b equals 0. And the other really useful fact that I'm going to use, which is slightly more obvious, is that if I put r into this equation, ar squared plus br plus c, then I definitely will get 0 because that's what a solution to an equation is. So I've got these two useful facts which I'm going to be using in a minute when I prove to you that this is a complementary function. E to the rx plus bx e to the rx. I'm using r instead of m because it's just going to help me in this proof a little bit. Okay, let's differentiate, see what we get. We'd get ra e to the rx plus, now we'd need the product rule, b e to the rx plus b rx e to the rx. Let's differentiate again. D squared y by dx squared equals r squared a e to the rx plus br e to the rx. Now we need the product rule again, so we get b r squared x e to the rx plus br e to the rx. Okay, let's put all of those into our original second order differential equation, which I'll just remind you was a d squared y by dx squared plus b dy by dx plus c equals f of x. And what I'm claiming is that if we put these into here, we will get 0, not f of x. That's going to come from the pi. We'll get 0. And that shows that a e to the rx plus bx e to the rx is indeed a complementary function. So we are taking a lots of the second derivative. I'm not going to bother with all of these e to the rx's, okay? I hope that's alright with you. Every single term that I'm about to write down has got e to the rx in, so I can just pull that out at the beginning, or not even, but I'll pretend I've pulled it out just to save me writing it down. So r squared a e to the rx plus br plus br squared plus br plus b lots of the first derivative, ra plus b plus brx plus c lots of the original function, a plus bx. Okay, let's tidy this up and see how much, for example, a we have. How much a have we got? Well, we've got ar squared, and then we've got plus br, and then we've got plus c. Oh, how nice, ar squared plus br plus c. How much bx have we got? Well, we've got, just realised I missed an x from that third term of that second derivative there. Just put it back in. So bx, how much bx have we got? We've got some here, we've got r squared, ar squared even, and then we've got some here, plus r br, plus, and we've got some here, plus c. Oh, we've got ar squared plus br plus c. Great. Right, what else is there that I haven't included? We've got 2br from that first term, and we've got b from that second term, and that's it. So this is ar squared plus br plus c plus bx ar squared plus br plus c. R is that repeated root that we found, plus b 2r plus b. For a second there I thought I had a problem, but I've just realised where I went wrong. When I expanded this out here, I should get 2abr, and I just wrote 2br. I didn't put the a in. So let's put that a in, which means I've got an a here, which means, phew, now I'm okay again. So ar squared plus br plus c. We know that's 0 because we know r is a solution to the auxiliary quadratic. So that's 0 and that's 0. What about our bit on the end here? 2ar plus b. Well, 2ar plus b is also 0, and we got that in a little complicated way, and we used the fact that r was a repeated root to get that fact there, that connection. So this is also 0, but only because r is a repeated root. So altogether 0. So that means our original idea of having a e to the rx plus bx e to the rx does produce a complementary function. It does equal 0 when we put it in the second order derivative.